Welcome back. I got an apple. It's an apple stream. Having one of those like just sleepy days, so I'm not gonna be in too long. I maybe have a meeting at 2. But I promised that I was going to start a kind of book club thing today, and I've got 40 minutes, so it's a perfect time to start it. Welcome to day 1. I'm going to be trying to do a few videos a day, because I'd love to actually do a bunch of book clubs while we're all doing this. Like, a little bit of information a day is a great way to learn something. So let's start watching some of these, and I'm gonna... Can I see it in like bigger view? Yeah.
There's a lot to learn about.
So, just quick credit to everyone involved. Primer is a YouTube channel. You can find it relatively easily. I enjoy their videos a lot. Haven't watched all of them. Haven't watched all of this series, but what I have watched I've really liked. Also credit to Free Blue One Brown, whose software they're using to do these videos. And yeah, I'll kind of pause and chat as we go.
Hi, this is the first video in a series about biology. There's a lot to learn about biology. Most courses start out with water, then you learn about organic molecules, and then you learn about how those molecules come together to form living things, and you go from there. And that's all great, but we're not going to bother with any of that, at least not right away. Instead, we're going to focus on evolution, because whenever you ask a why question in biology, the answer always comes back to evolution. And we're going to spend a while on evolution. It's going to be 10 to 15 videos. We're going to take it slow, and we're going to use simulations and math to really understand it.
So this is a perspective which really chimes with me on how to go looking at biology. I studied biology a bit going through school. When I went to university, I actually stopped before I finished school, and then at university I started again with a course on evolutionary biology. I've always had a bit of a passion for it. And there are fantastic mathematicians who are doing biology, and lots of fascinating mathematics in biology, but sometimes it can feel like, particularly in the way it's taught at like some undergrad levels and school levels, that biology is sort of a-mathematical or anti-mathematical, and that really isn't true. And for understanding stuff like the biological evolution of systems that we're seeing right now in the world, that's a long way off true. And that's why I think this is such a great first course. It's a good first course for like 5 different things. It's a good first course for evolution, it's a good first course for mathematics, a good first course for biology, it's a good first course for YouTube learning.
In the spirit of taking it slow,
good,
let's
folks.
zoom out and talk about things in general, including non-living things. Why do things exist? You could answer this question in a number of ways, but the answer that we'll use has 2 parts. First, things that exist have started existing, or they've been born. Second, they haven't stopped existing yet, or they haven't died. It kind of seems like we haven't really said anything, but great.
I also love this, like, when you put it into words, a mathematical description of the universe is often almost bizarrely and difficult to conceptualize how simple it is, but yeah. This is a great, quite esoteric, but also immediately usable definition of why things exist.
Breaking it into 2 parts does help us look at some patterns. For example, raindrops. Why do raindrops exist? Well, they're good at this first part. They're good at being born. They don't last very long, but they form pretty often enough where it's not unusual to see them. A different example is planets or stars. Unlike raindrops, they don't form very often at all, but they more than make up for it by lasting a long time. When we look up in the sky or just at the ground, we see planets and stars. They're also common even though they do it in a very different way. Any kind of thing that exists strikes some balance at being good at one or both of these two things. So this is all well and good, but as promised, we can make it a lot sharper by building some simulations and an equation. This blob creature will be the star of our first simulation. At each frame in the
He's a good
simulation,
blob.
one of these blob creatures will form, and each living creature will have a 1 in 10 chance of dying.
So,
For comparison, let's make a second simulation with this other type of blob creature. Compared to the first kind,
We'll see a lot of
this
these
blob
blob guys.
creature will be more like a planet. It'll
that's
form less
working.
often, but it'll also die less often. Each frame, there will only be a 1 in 10 chance of one of these forming, but each blob creature will only have a 1 in 100 chance of dying.
So maybe not too surprising.
After
I think
watching for a while, you can
I'll talk just quite a lot about like, general mathematical thinking, and I think one of the things that you quickly learn from mathematical exposure is that often it is a ratio, or some ratio of all the numbers involved that is more important than the actual definite number.
see that even though
That's
these
very
two
much true
kinds
here.
of blob creatures are quite different, on average, there's about the same number of them at any given moment. You might be able to guess what happens when a kind of blob creature has a low birth rate, like a planet, and also a high death rate, like a raindrop.
Oh,
There
poor
just aren't very
thing.
many of them. At the other extreme, if a kind of blob creature has a high birth rate, like raindrops, and a low death rate, there will be a lot of them.
So you might even
Why
notice,
do these
and this will kind of be expanded on as we go, that the total basically hangs around the ratio of the two.
simulations seem to
And-
stabilize around a certain number of creatures? You might already have some intuition for this, but we can translate that intuition into an equation which will let us predict the equilibrium number for any birth rate and any death rate. If the total birth rate is equal to the total death rate, we'll expect the population size to stay the same from one frame to the next. And since each creature individually has a chance of dying, the total death rate depends on the current number of live creatures. Using numbers from our first simulation, where one creature was born each frame, and each creature had a 1 in 10 chance of dying each frame, we can see that the expected birth rate and death rates should be equal when there are 10 creatures.
And this
And
indeed
that's
is
what we
why.
saw in the simulation. But we also saw in the simulation that the number of creatures fluctuated all over the place. It didn't just stick at 10. It's possible for all of the creatures to get lucky and not die, in which case the number of creatures rises to 11 in the next frame. But then the expected death rate will be higher than the birth rate, and then on average we'd expect more than one creature to die in the next frame, which would push the number back toward 10. Of course the creatures could keep getting lucky, but the more creatures there are, the less likely it is.
So, just to be clear, at this stage, these aren't creatures that are living out any kind of life or reproducing. They just each individual, like they don't care how many other creatures there are. They're just playing their own little game of flipping a coin, and if it lands one way, they're created, and then every turn they flip a coin again. Like a coin. Coins are very hard to not make 50-50. Maybe it's better to say they flip a some number of sides dice. Flip a 10-sided dice, and if it rolls a 6, they die. So there's no competition for resources, there's no dependent, because there are 14 creatures doesn't change the chance of the creatures living and dying, even though there's only 10 as the equilibrium. But those individual chances do still mean that it will
It's
hang
also
around
possible
near
that
10.
more than one of them will get unlucky and die, leaving us with fewer than 10 creatures. But if this happens, the expected death rate is suddenly lower than the birth rate. So in the next frame, we'd expect the population to drift back up toward 10.
Although there is this nice factor that the death rate, and this is what he's describing right now, is the number of creatures alive right now times the chance of them dying. So the death rate increases as the number goes up, but the birth rate is they're just popping out of nowhere, so the birth rate is constant. So whether you can do it. Hence why, if the death rate gets large, if the number of creatures gets large, so if we have, I think we'll see some of these graphs in a sec, number versus time, I guess we're kind of actually doing it in steps, but let's call it time, let's have a nice purple colour. Let's say it starts with 0, there's absolutely no way for them to die, because there aren't any of them yet. Some start being born, a few die, but they tend to be born. Then, if this is the equilibrium, they can go above it, but right now, because n is larger than the equilibrium value, they're going to drop back below. Well, they may not drop below. This is a random process. It doesn't obey any particular certainty of law, and I think that's something that is quite different dealing with statistical things than the way we often like to think about science and engineering, that it's kind of false. The things certainly happen and that one thing certainly follows from another. So it is completely possible, just more and more unlikely, that this number will always be larger. And, well, not always be larger, but always is a kind of undefined concept. Will be larger at some point in time. It is also completely possible, and the system doesn't really care, for this number to just happen to be 0 at one point and just come back up.
The fancy word for a balancing situation like this is equilibrium, and 10 is the equilibrium number of creatures for the first simulation. Going back to the more general version of
So
the
this here
equilibrium,
would be
we
our
shorten it up by
equilibrium.
using letter symbols instead of the full words, and we could solve for n to get a formula we can use to predict the equilibrium number. So now if we set up a new simulation with a birth chance of 80% and a death chance of 2%, what equilibrium number should we expect? Well, the formula tells us it should be 40, so let's see what the simulation does. Looks about right. Alright, so what does this have to do with living things? From what we said so far, it kind of seems like we shouldn't exist. We're too complex to form spontaneously the way raindrops do. Imagine all the right atoms and molecules just happening to come together to form a rabbit. It's pretty unlikely. And we also don't live all that long. But somehow, living organisms are still pretty common. So what's going on? Now would be a good time to pause and think for a second.
Alright, I kind of know the answer, so this is cheating, but yeah, let's take that. That inspiration, because it's true. Like, how do we get something as complex as a me that thinks, hey, it'd be a good idea to broadcast this on the internet? Also, there's something as complex as the internet. This kind of magic popping into existence certainly can't be true. And this is a question that I think, maybe you're like, this is a really good question, I want to think about it. For some fraction of people watching this may be like, this is easy. The answer to this question is easy. It's just evolution. It's random change over time. But I think something that is worth thinking about, if you haven't thought very deeply about evolution before, is how far can you get with random changes over time? How big a jump can a random change be? And what limits that or accelerates that? Because there's a lot of shapes and sizes that humans could be, or the thing that plays the role of humans could be. Why do we happen to be the shape and size that we are? And the answer is almost always that we're pretty close to something locally optimal, or even that we are continuously kind of going uphill or downhill, whichever way you prefer to think about it, to some optima. Maybe we reach an optima, sometimes we hang out there for a while and then we get pulled away again. It's going to take a while to get to that kind of complexity in these simulations, because that reaching an optimum going forward requires changing conditions, and it requires like quite a nuanced set of stimuluses versus circumstances, but we'll get there.
Alright, ready for the big reveal? As you may have guessed, living things are special because we can make more of ourselves. We have an extra parameter in our simulation, a chance to replicate. So let's add replication to our equilibrium equation. Just like before, we're looking for a situation where the birth rate is equal to the death rate. The overall death rate is just like it was before. It's the number of live creatures times the likelihood of each creature to die. The overall birth rate is different though. We still have this B, which stands for the likelihood that a new creature will spontaneously pop into existence like a raindrop. But we also have this extra piece to account for reproduction. This works just like the overall death rate. Each creature has its own chance to reproduce, so we multiply that chance by the number of living creatures to get the total number of births we expect from reproduction each frame. The significant thing about this equation is that n is on both sides. Before, just the death rate went up as the number of creatures grew, but now the birth rate also grows as n gets bigger. To see this in action, let's solve for n and look at a simulation.
So basically, another way of putting this is we've now got this is a constant plus
We'll start our simulation
times
with
R.
two creatures. The spontaneous birth chance each frame will be 10%. That's a lot higher than it would be for an actual birth, but we only have so much time in this video. And the death chance per creature each frame will be 5%. For now, we'll just leave the replication chance at 0. Our formula tells us that the equilibrium number of creatures should be 2, though it's a bit hard to see in this simulation because of the fluctuation. Anyway, if we bump the replication chance up to 1%, we see the equilibrium number go up to 2.5. Not a huge difference, but as we push it higher, the equilibrium number goes up by more and more each time, and we can start to see the effect in the simulation. And you might notice that we're about to run into an issue. If we raise the replication chance to 5%, we'll be dividing by 0, and there won't be an equilibrium at all anymore. The population will get bigger and bigger without limit, and if the replication chance goes higher than the death chance, our formula gives us a negative number for n, which makes no sense because we can't have a negative number of creatures.
So let's look at this graph of the equilibrium number as a function of the replication number. So we're looking at the equilibrium number, which is the birth chance. Oh, I guess in this language it should be little b. No, it literally is. It's the birth rate over death rate minus the equilibrium rate. So when it's when the replication rate, which is what I'm going to put on the x-axis, is 0, this is just b over d. And then as it grows, I'm going to put d here. So this is the point where the replication rate is equal to the death rate. Are those going to appear? Yeah, there we go. As it grows, d minus r is getting smaller, and so let's have another different colour. This gets larger and larger and larger quite quickly, and goes at d up to infinity. So the equilibrium number gets huge pretty quickly. Then what does it mean once it goes past that? This number is actually negative, and it ends up looking like this. Often when you're learning maths and physics, you find these negative kind of roots all the time, and we kind of throw them away. I would argue that they are almost always that's bigger than I expected. Almost always meaningful, almost always interesting, but potentially also, in some cases, uh, they can muddy your interpretation. Not because the physical system doesn't have that in it, but it is often actually telling you about a case, like it's telling you more about your setup for the equations than the actual behaviour. So a negative number, I think one of the best ways to see it is, what if we reversed all of these, and what if we look backwards in time? Such that every time something replicated, a bunny disappeared, and every time something died, a bunny appeared. Then this would be the equilibrium number in that case. Well, another way of looking at this is it's telling you how far back you would have to go to be at equilibrium. Equilibrium is unattainable because we can't go to negative time, but the extent, the size, the distance, difference in distance here and here is meaningful and does have some mathematical.
And even if we could, the number of
Clamps.
features is clearly going up and up and up and not getting closer to that negative number. Reproduction quite literally breaks our equation. This is why living things are special. They follow their own set of rules, which makes it possible for the complexity of life to exist. The rest of the videos in this series are going to explore the consequences of this, which are collectively called the theory of evolution. See you in the next video.
This is quite a different construct than the theory of evolution posited by Darwin. Like, the translation of this into mathematics, although it always had some mathematical components, the turning of it into a kind of full, some could say, and I think this would be reductive, physics look-alike mathematical system was something that people had to come up with. Like, you have to choose to represent something in mathematics. Just while I was finishing that thought, and I think this is the last thought I'm going to leave us with, another way of looking at what this means is that it's how far back in time you have to look for the thing to be at zero, and that's why this number is getting smaller and smaller, because as the replication rate gets faster and faster, the population grows faster and faster and faster, and so if the growth is pretty slow, you have to look quite a long way back to find equilibrium. Whereas if the growth is immediate, like if the growth is huge, just blowing up, you have to look almost no time at all back to find equilibrium. And that's what these numbers over here mean. I hope this was interesting. I'm going to keep doing it because, got to fill your days with something. Keep on checking in. You can find these on YouTube yourself, watch them at your own leisure, and I'll probably come back tomorrow and watch another one, talk about it then. Alright, see you then.